Eddie, please introduce
Good.
yourself and tell us more about who you are.
Yeah, so I'm Eddie, one of the co-founders and CEO of Astron Systems. So we're a company based in the UK and we're working on the first completely reusable small lift class rockets. So you've probably heard of some of the really big rockets in development that also are turning towards full reusability, people like SpaceX and Starship. Actually, big rockets aren't the whole market, they can't serve every need. Small rockets are also important and they need to be fully reusable eventually as well. And we think there's a very compelling way of doing that we're working on that can do that now.
Fully reusable small lift launch is widely viewed as uneconomical. What do skeptics get wrong?
Yeah, so I think there's kind of a few things there. So I think definitely the skeptics getting it wrong don't understand the kind of driving unit economics of what actually drives the cost of operating launches. So there's kind of two big dimensions that you kind of need to realize drive a lot of the significant cost of the launch of a rocket. So one of those is your fixed costs that your business operates with. So this is kind of all your staff, your payroll, overheads, paying for your facilities, rent, all that kind of stuff. And this you have to pay pretty much regardless of how many rockets you're launching, how often you're launching them. So the kind of cost contribution you need to pay as a business towards paying off those fixed overheads per launch then is obviously sensitive to cadence. So if you're spreading it over one launch a year, that one launch has to cover all of those fixed costs. If you're spreading it over many launches, it's much less. To the point where if you had infinite launches, it's basically zero. So there's that element. And then there's also the actual direct operating cost of that launch, the marginal direct cost of operating that launch, which is much more driven by the cost of the vehicle, the cost of operating that vehicle, your insurance that you've got to have, all of these kind of things. And so for a fully reusable vehicle, the kind of fixed cost to a first order shouldn't really be any different. You're going to still have typically a similar number of people, maybe even actually less, because you don't need to have quite as high of a manufacturing rate for the same flight cadence. And so this kind of fixed cost, which is kind of cadence sensitive, actually is probably quite similar. And a lot of people go, oh, with reusability, there was this kind of myth spread by Ariane Group back in the day that you need cadence to somehow make reusability worth it. Well, that doesn't actually hold up. For the same kind of fixed cost base, the same kind of cadence, it's going to work out. That contribution, the same. The other one, which is the kind of cost of the actual operation of that flight with that vehicle, that doesn't actually depend on the cadence. That depends on how much can you manufacture the vehicle for, how many flights can you spread that cost over. If you are spreading that cost over multiple flights because you're reusing it, what actually is the cost of then operating the recovery portion of that flight and the refurbishment portion of that flight compared to the cost of manufacturing, assembling, qualifying for flight, and then transporting to the pad entire new rocket stages. And if you look at things like propulsive landing and operating landing barges offshore, you could maybe make an argument you can build small rocket stages, potentially if you really, really make some optimistic assumptions, lower cost than operating those. But if you take out that constraint of doing propulsive landing on barges offshore and think of lower cost ways to recover your stages, and if you can find ways to bring the refurbishment cost down with technologies that don't need extensive refurbishment between flights, very quickly you end up in a situation where, of course, it's dramatically lower cost to have something that's reusable and you spread that cost over, say, 100 flights, than the cost of that rocket being spread over one flight. And that's where we've got to get to. Plus, the whole thing we're not mentioning on top of that is there's also a market for returning payload from orbit, where people also pay you to do that. So there's an extra incentive on top of it being lower cost and better, is you also get extra money from customers because you can bring stuff back as well. So the question is, why shouldn't you reuse the whole rocket?
You are targeting 5x lower cost and 10x faster launch readiness than rideshare. What single engineering or architectural design unlocked that shift?
Yeah, so in terms of, I think it's a whole separate conversation of rideshare versus small launch, and then there's a conversation about why what we're doing is lower cost. I think the main thing about what makes us lower cost is we are compared to say let's say existing small launch, so Rocket Lab and Electron, is that complete reusability. So we're taking that cost of that vehicle, which is typically of the order of millions, and we're spreading it over many flights, and we're doing it with a low cost system for the recovery and for the maintenance. So with the recovery system, one of the things we're doing that's quite different to some of the bigger vehicles is we use a power foil to slow down that stage, and then we're going to go get it with a helicopter. And the operating cost per flight for a helicopter is a lot lower than for a big barge you're going to go send out overseas, which is going to be of the order of a few 100,000 to do per flight. So that helps bring the recovery cost down. Now, the other thing you need to do is have a system where you don't need to refurbish the vehicle extensively each flight. And there's two big areas there. So one is the engines. So typically this is one of the highest wearing ones, and it's very hard to actually build long lifetime small rocket engines. If you just look up a textbook conventional design for rocket engine, do it at the small scale, you find very quickly that the wear and tear is quite bad, and it doesn't really last many flights without lots of maintenance. So that's a challenge you got to solve. And the other one is, of course, getting the thing through the atmosphere with a heat shield that is going to work for multiple flights. That's the other really big challenge you've got to solve, where we think we have pretty good approaches to. The whole other conversation we can dive into now, dive into a minute, then is rideshare versus small launch, but I think that's separate.
You have hundreds of millions in LOIs and over $1 billion in informal interest. What are customers signaling that the rest of the market is missing?
Yeah, so I think it's always a very easy sell to customers. If you say, hey, if we can get you to space, to orbit where you want to go, and do it in a way that's faster, cheaper, better, more sustainable, the answer is pretty much always a yes. So I don't think it's particularly surprising. I think what is maybe surprising is that some customers are saying yes, and we're still quite a long way from launching, which kind of shows how much demand there is for this out there in the market. Plus, of course, the capability for returning from orbit is also a lot of customers are quite excited about. So things like bio and pharma, these kind of topics as well. So yeah, I think there's definitely a huge market for small lift launch. I think actually this does kind of tend into, we might as well address the elephant in the room now, which is this rideshare versus small lift rockets. So if you're talking about rideshare on these bigger rockets, what you're not realizing when you're paying your launch cost necessarily is there's also a cost of actually getting that satellite into its final orbit where it wants to operate. Now, obviously, it depends on the satellite and the mission, how much they care about that or where they want to go, but a lot of companies and satellites do care about that. So say, for example, you want your satellite to do something interesting, you're going to want to generate of the order, well, let's say for theory's sake, you're generating of the order $5 million a year revenue with that satellite. Let's pick that arbitrarily as something that seems you might be able to make some money with. Well, if you turn that to per day, that's something like $13,500 a day of potential revenue that you could be getting from that satellite when it's operating in its exact orbit position it wants to go in. So if you then launch that on a rideshare mission, even if that's completely free, you've got to move it to there, which, let's say we do the electric propulsion, let's say that takes 8 weeks, that's now another $750,000 that we've essentially wasted moving our satellite to that position. That's one factor. The other factor is we want to be able to launch exactly when a customer's ready, because we can have a mission that's tailored specific to them. And so, again, if you take that example and say it's 6 weeks delay between it coming at your factory ready to go on the spacecraft, on the launch, your spacecraft is manufactured, versus when it's actually launched with a rideshare, even if it's just 6 weeks, that's already north of $500,000 that you've potentially wasted, versus if you had it ready and straight on or lock it and actually put up into space when you want it. So where you want to get it deployed to matters, when you want to get it deployed to also matters, and even more so, the other thing is it costs propellant from your satellite to get it to that position when you're doing that orbital deployment. So the propellant typically might be of the order about 30% on your satellite is used for that kind of orbital insertion. If we took that instead, let's say we had a baseline lifetime of about 5 years for our satellite, and we took that 30% of propellant and instead used it on expecting to station keep and have a longer lifetime, now we're talking we could be adding another $10 million of potential revenue from our satellite. So you can very quickly see that if you have the right mission sets and constraints, it actually really pays to be dropped off where you want to go, when you want to go, and that's today why people pay the comparatively extortionate prices of small lift rocket launch with Electron and Rocket Lab, which is about $25,000 a kilogram, $7-8 million per flight. And so you kind of change the cost of doing that dedicated service on a small lift rocket, make that lower cost, make that service even better, even more responsive to when customers want to go and where they want to go to, then actually the number of missions where you choose the small lift rocket only increases. That kind of business case of when you're saving money to make it worth it only gets more attractive. And so very quickly becomes, why wouldn't you want to launch on this mission? Why would I want to go and have to deal with moving my satellite and spending propellant, spending cost, and not being able to launch it when I want to launch it? If we're talking about something like Starship, you're talking about something that can launch 100 tons at once. If my satellite's 10 kilograms, I'm not getting a dedicated Starship launch. even if Elon's very optimistic with all his cost assumptions for how much that is to operate, that's still going to cost way more than getting a small lift rocket that's also optimized for reusability. So there's very much a need for both. And that's, I think, the big thing there.
Your hybrid electric turbopump claims 100x lifetime improvement at this scale. What is fundamentally different in your design that enables this?
Yes, so that kind of goes back to one of those things I mentioned earlier, which is the rocket engine really needs to last for many flights. Well, they might ask, why? Why can't I just swap out my engine? Is it that expensive? Well, the answer is yes. So typically, in a rocket, your rocket engine or propulsion system is something like up to about half of the cost of a conventional rocket. And so if after 1 flight, 2 flights, 3 flights, you're replacing your engines, you're not getting a lot of the economic benefit of that reusability. You couple with that what I was just saying, that small rocket engines are quite hard to make really reusable, you have a challenge to making this work. And so if we look then, where is it that engines are typically hard to actually get that lifetime out of? So you have, within the combustion devices, there's fatigue. That's a problem. We can model, we can design them carefully, we can work around that. So that's your thrust chamber. But the other areas we have challenge is in the turbopumps, which are what take your propellant from the tank and they pump it up to the pressure needed to then insert it into that combustion chamber for it then to combust. And these essentially have to spin very fast, high pressure, all these things. Typically also having the turbine fed from some hot gas that could be coming from a pre-burner. Some cycles, like the expander cycle, it's just from a heat exchange with the thrust chamber, which then drives that turbine. If that's also being combusted, that also has soot that can be generated. That can build up. That can cause problems as well. So there's a lot of challenge in getting these turbopumps working, especially at the small scale, because when you shrink down these things to the smaller scale, what you find is the speed at which you have to operate at goes up just because of the scaling of the physics. So small rocket engines fundamentally very different and difficult compared to big rocket engines in different ways to get the reusability. And so within that turbopump, the kind of 2 big sources of where you end up with is the seals, because you need to keep the fuel and the oxidizer separated. Conventionally, you have 1 shaft, you have a turbine and the pump for the oxidizer and the fuel all in 1 shaft. You've got to keep those things separate. You don't want the fuel and the oxidizer mixing in the wrong place, things go kaboom. That's how you get failures. People like RFA had a turbopump failure on a rocket stage not that long ago. I don't know exactly the cause, but could speculate could be a seal failing or something, or one of the other things we're about to talk about, which is the bearings. But essentially, we have a different approach where we take our turbopump, we split it up completely mechanically separate for the fuel side and the oxidizer side, but we still also have a turbine in there. So on the fuel side, it's 1 shaft that has fuel impeller and fuel turbine. And on the oxidizer side, it just has the fuel impeller. And then we couple them electrically with an electrical transmission. So we're completely eliminating any source of mechanical wear or failure where they could mix at all on any shaft. And then the other big area with wear is on the bearings. So again, because these things are spinning faster and the fluids you're pumping through these are not particularly great for lubrication of bearings, the lifetimes of these bearings is typically awful. So if you have roller element bearings on a conventional design turbopump, we did a baseline design for our kind of engine scale, what we thought we might be able to get as lifetime. You end up with about 10 minutes of 99.9% reliable lifetime, which is plenty good enough if you want to do 1 flight. Maybe you could argue you might want a bit better, but you can probably get a good enough reliability. But if you want to do many flights, that architecture doesn't really work out. You're very much going to have problems. So the other thing we do, in addition to separating mechanically the units, is within each of those, we also have hydrostatic bearings that are taking kind of tappings off of some of that fluid that we're being pumping, and we're injecting it in to the unit in these hydrostatic bearings to then use the fluid pressure to actually support that shaft and alleviate a lot of the load on the mechanical roller bearings. And the effect of that pushes up that expected lifetime to more like tens of hours, which is the level needed to be able to then fly these missions 100 times without needing to go and replace your turbopumps, which, by the way, are the most expensive, typically part of the engine. So that's kind of why we have the approach we have with the hybrid electric turbopump. Plus, we're using methane and oxygen, which, again, doesn't cause soot, and we also don't have a pre-burner before the turbine. So, again, we're not having any soot able to build up on the turbine. So our engine is doing everything we can so that eventually we shouldn't need any inspection, any maintenance, flight to flight.
Without Astron, how do small sat operators access orbit today, and what is the true cost in time and lost mission value?
Yeah, so I think this goes back to what I was talking about a minute ago with the rideshare versus dedicated launch kind of philosophies and the differences there. I could say the same thing again, or I guess rewind and watch that bit. What I will add, I guess, is there's other ways that kind of fit as an intermediary. So there's, yes, this ability to rideshare. There's, yes, also this ability to get a dedicated launch. There's also the ability to take a rideshare mission and have someone else move you from that place that you get dropped off from your big SpaceX Starship or Falcon 9 or whatever it is and put you where you want to operate. And that's an interesting one because that's kind of the business model of a number of companies like Deorbit, Momentous. They have these tugs. That is one that works quite well at the moment with the pricing of things, but in the long term, I think we'll see being less attractive. So for one, the tugs can only get you so far. They can't actually change orbit hugely. That still takes propellant and cost and all these things. But the other thing to realize is the tug itself needs to be launched and needs to be built, and there's a real cost to that. So if you're launching a kilogram of satellite, you're probably going to need a kilogram of tug along with that. So a baseline is doubling your launch cost per kilogram is going to go up. Plus, the cost of these tugs themselves might be of the order about $1 million to produce. So very quickly, you can see if we have a tug that's going to be quite hard to then reuse because it's up in space and how you're going to get it back down and refly it. Actually, quite quickly, you can see if you have a fully reusable small rocket, you can quite handily beat the expected cost of that. So if you want to put some actual numbers to it, right now, the dedicated small lift option with Rocket Lab is costing you about $25,000 a kilogram as a customer price. If you're going with a space tug on Falcon 9, right now you end up about $15,000 a kilogram. But with launchers like ours, we'll be able to go well below that on pricing with a dedicated small lift rocket, in which case that kind of shifts. And does it then make as much sense to have that service? For a lot of missions, no. Some, it still probably will make sense, and obviously small rockets can only go so far in terms of performance, in terms of if you want to get to higher orbits or want to go to the moon or do other interesting things. We're not going to be able to do that. So they still have a good kind of use case, but this kind of dropping off and deploying of satellites as a last mile is maybe less attractive for at least the low Earth orbits.
And to continue to double click on the conversation of rideshare, SpaceX rideshare is nominally cheap. Where is the actual bottleneck that creates a durable wedge for Astron? Maybe we can just continue to dive deeper into what you've kind of communicated already.
Yeah, so the kind of edge that makes people already pick small rockets, as I said, is only going to keep growing if you make the small rockets more attractive. The number of mission sets where that extra burden, that extra cost coming from that burden of having to reposition your satellite, spend the propellant, which is also lifetime, and also wasted revenue, spend the time to actually maneuver, which again is wasted revenue, and not have your launch when you want to have it, which again is wasted revenue. That very much pushes people towards having more like the private jet or taxi-like service rather than going for the let's have a bus or a big A380 type commercial airliner service. So that's kind of one thing that's a very sustainable long-term need, that there's always going to be need for small lift rockets for that use case. The other kind of angle that's also there is also for the defense side. So if you want to have something that launches at short notice for defense payloads, which the defense industry really want, you can't really beat a small rocket for that. One of the advantages small rockets fundamentally have that others don't have is you can, near enough if you design them right, fit them in shipping containers and move them around. And that's one of the things that we build too, is we have each of our boosters, a booster and upper stages able to fit in shipping containers. So we can do that, which gives you geographical resiliency, which is something that's quite important to the likes of Space Force and other defense customers. As well as, of course, we can then short launch on short notice, which, again, you could theoretically do with something like a Starship, but it's going to cost you a lot more than with something like a our-size vehicle.
You are positioning for tactical responsive launch and rocket cargo deployment. How real is defense pull-through, and what specific requests are you hearing?
So it is very real. I mean, it's no secret that the likes of US Space Force say they want rocket cargo, say they want tactically responsive launch. We were invested in by Techstars Space last year, which is partnered with the US Space Force. We know some guys over there who quite like the idea of what we're building. Also, even more concretely, there's also another company, Shield Space, who spun out of the UK Space Command, who's actually one of the customers booked to launch with us in the future. So that's another very specific defense use case. And we actually co-presented with them at a NATO dual use space research specialist meeting about a couple months ago. So yes, there is very real need for defense space launch capabilities and for them to improve, both for, yes, that tactically responsive side, yes, that rocket cargo side, but also on the kind of responsive side, you need that kind of geographical resiliency piece. And also you don't just want a vehicle that you launch once, but also that you can then use multiple times, because if you have a sustained threat, you have these kind of things going on up there you want to respond to, not just once, but again and again. Then you're going to need a rocket that you can launch again and again, or you're going to need to stockpile a lot of rockets. And stockpiling a lot of rockets is expensive.
Short cycle microgravity, 20 to 50 hours, is a novel service. Which segments, pharma, materials, defense, need this first, and why?
Yes, so our upper stage obviously does come back from orbit. That's kind of the whole thing with reusing it. And that kind of necessitates that it has to stay up there for a certain amount of time to be able to do that anyway. And if we're talking about polar orbits, that's going to fall in that range of 20 to 50 hours. So without adding any extra requirements, we can stay up there 20, 50 hours. We can ride along secondary payloads to come up and use that, which is attractive for a lot of customers. Like you mentioned, there's people with pharma like BioOrbit, Frontier Space, Vardo, and others. And also on the material side, people like SpaceForge, all who are going after this market for manufacturing or doing research and development in space. Plus, there's a whole other one which people maybe don't talk about as much, which is space people building and testing things in space. So if you have a new Hall thruster or a new material for your satellite or whatever it is you want to get an in-orbit demonstration of, wouldn't it be great if you could quite easily and cheaply get it up in space, have access to essentially a vacuum chamber, the real space environment, everything, test it, and have it come back a couple days later? That's pretty good, especially
Brilliant.
considering the cost of some of these other facilities you might be using on Earth. It actually starts to be quite attractive. But that's the short duration. We can actually probably push up to quite a bit longer duration. We have challenges that we have cryogenic propellant and boil off to manage. It's doable with methane, unlike hydrogen. Obviously, Starship's looking to go to Mars with a methane architecture, but there might be some compromises you have to make to be able to stay up there, and it'd probably only be for like a couple of weeks compared to some of these free flyers. One of those, for example, is to do some of that boil-off management. It will depend on the orbit we're in, exactly how we're able to do that, and we might, for example, have to make certain maneuvers to change the orientation we're in to be able to effectively do that, because we have a heat shield on one side. It'd be really good if the big insulating side is against the hot thing, essentially.
And for our
Whereas the free
audience,
flyers don't necessarily have to do that and can stay up there for months.
boil off management is
Yes, so cryogenic propellant likes to boil off if you heat it up. Essentially, the way cryogenics work is that it will, on its own, like to boil and create a high pressure, which eventually would exceed your structural limit for your structure and then explode. So to prevent that, what you do is you vent off a little bit of the gas as it boils. That cools it down, keeps it cold, keeps it from exploding. So you have to keep venting off a little bit over time to manage that. Now, space also is quite cold. So if you're careful, especially with something like methane, you probably don't need to vent off that much, potentially even not at all, depending on your exact orbit, how you're able to point to it, heat transfer, etc., etc. With stuff like hydrogen, it's very hard because its boiling point is so low, but actually methane is not too bad. But depending on the mission, there'll be a boil-off rate you have to manage.
what is the largest remaining technical or execution risk, the factor most likely to influence timeline certainty?
I think there's a lot of things that can influence that. I mean, there's a lot of execution still needed ahead of us. We're still a fairly early company in that kind of journey. I think the biggest one is probably not the technical side. It's probably how quick can the money come in? Because if you actually look at typically what drives how fast a lot of these companies move, more so than the technical side, that does often play a big factor, is also how quickly they can get the money in. So if you get really big amounts of money in really quickly, you can move a lot faster on a lot more things in parallel, versus if it comes in smaller amounts, well, that's kind of what you saw with, I guess, the early days of Rocket Lab is from, I think it was 2006 or something they founded, correct me if I'm wrong, to up to 2013, 14. They were kind of just going along steady. They were doing little bits here and there. And then 2013, 14, they got quite a lot of capital behind them. And then by 2017, they were launching electrons into space. So that's probably the biggest lever, which changes how fast we can move. If everything goes super smoothly, we can move much faster. Obviously, the technical side The big areas is continuing to finish working on our rocket engines so we get a full engine working, so second generation of the turbo machinery, our thrust chamber, that coupled together, and then moving towards flight versions of those, as well as then on the heat shield side, actually getting that built out specific to our vehicle. We're actually able to pull in some pretty good heat shield technology that Europe's been developing. Quite interesting, actually, of its own right. So we're not as worried about the heat shield side, but it still needs to be kind of done for our vehicle and then obviously eventually flight proven. So there's a lot that needs to go right, but it's all very doable within the rules of physics. It just might take a bit more time or money to get there.
Your first test launch is targeted for 2027. What must go right between now and that milestone to stay on schedule? And I think you've answered that, but maybe I'll give you another opportunity to double click on that.
Yeah, so we are now targeting 2028 for first flight rather than 2027. That still does rely on that kind of capital piece coming in sooner rather than later. Otherwise, very quickly, that's going to get pushed to the right a bit more. But yes, that's the main thing. And then how effectively we can then get all of those things developed exactly on the kind of schedule we say, because that's the green lights to Malibu, let's say nothing goes wrong timeline still. So it's very much, realistically, we could be looking 29, 2030 by the time we add some realism factor in.
If Starship scales and achieves its pricing roadmap, how does Astron still win? What is your durable competitive advantage?
Yeah, so if Starship scales and works, which I actually kind of hope and think it hopefully will do, it kind of comes back to what I said about earlier. There's an inherent difference between a rideshare and a dedicated launch. And Starship is not really going to serve small payloads for dedicated launches, both for stuff for the satellites going up there, also if you want microgravity, maybe, but also even then, we can do that as well on the small scale, on your timeline, get it back in a couple of days. So that's kind of the big defensible advantage, is that Starship, if you look at Payload Space Report, they forecast, based on Elon optimistic numbers, they then say that we probably recommend about $10 million marginal cost per launch for Starship, which is very impressive for something that big, and consider the payload, dollars per kilo, that's amazing. Our expected long-term marginal cost is more like, if we hit all of our targets, and this doesn't include profit for people and this kind of thing, but like the actual marginal direct actual cost of operating, probably of the order 150 to 200k is what we think we can get it down to. So that's the advantage, is it would just cost less. It's like a taxi versus a really big bus, or a regional jet versus a really big A380. There's a very distinct market for both.
Lightning round questions. Why does space matter?
So space matters for everyone, probably way more than most people realize. You probably already know the answer. Everyone else maybe listening, if you know the space industry, probably does. But satellites are hooked into all of our daily lives in ways that we don't all necessarily realize. The obvious one everyone talks about is GPS. There's also position, navigation, and timing, which is used for things like banking transactions and other things beyond just GPS from the kind of PNT side. There's other interesting ways that I think not everyone's as aware of. So again, a lot of Earth observation data actually has really, really good uses. And one thing that is an issue that I think I care about quite a bit, and I think a lot of people care about, is also the environment and what's happening to our planet. And that the kind of fundamental bedrock of everything that happens to our planet, and our understanding of all of climate science comes from a lot of satellite data. A lot of those kind of environment change variables that we monitor, the majority of them rely on space data. So without that, you don't know what's happening. And also, increasingly, you can use that stuff for enforcement. So something interesting that I guess MethaneSat was doing is then using that to point out where there's emissions on the ground and of methane, which you can then cut, because that's probably one of the single biggest impacts you can make for climate change. That's probably the biggest opportunity we have actually for, in the near term, the next kind of decade timescale, having an impact on the heating of our planet is cutting methane emissions. And guys like MethaneSat, which unfortunately stopped working, and GHGSat, which is kind of standing up there now and doing it with small sats, those can help do those kind of applications and enforce these things on the ground, which mean that maybe we have a planet that still is inhabitable in the next 50 years. So it's important for all kinds of reasons.
For our listeners, what is the one thing or a few things that you want to make sure that you're sharing? Our listeners might be other founders, they might be potential talent, they might be investors, and they might be, again, individuals that are not exposed to space, but they're in adjacent fields like engineering, geothermal, welding. Do you have anything to add as we close up?
I think the main thing is that this is all doable. We can all do this. I think, especially maybe sometimes the mindset in UK, Europe is, oh, this feels too ambitious, too crazy. Let's do the safe thing. But I think too often that comes at the kind of sacrifice of the commercial side. So there's probably way too many companies out there right now building rockets that look very similar, expendable, but maybe they have the flag of the nation they're in, but maybe it's better because we optimize some manufacturing process someone hasn't thought of before somehow. But actually, really, I think you can sometimes swing a bit bolder than that when you need to for the technical side, and it can work and does work. I mean, that's what got SpaceX going back in the day and was like, oh, it's crazy doing booster usability. Actually, now you look back, it's crazy not doing booster usability. So I guess have more confidence, have more conviction to actually sometimes take the steps needed when you can see they can be done, because commercially you can see it can pay off.
And what motivated you to get into space technology?
I think the thing that motivated me, so I've always loved sci-fi, so things like Star Wars, Star Trek, love Star Trek, these kind of shows. Also, The Expanse is another favorite of mine. So that was interesting. And then also, I think what kind of specifically drew me in is I started playing many years ago, as probably everyone in the space industry has, Kerbal Space Program. This is back when I was in like high school, and doing missions in that, playing with rockets. I was like, oh, this is pretty cool. At the same time, you could see the rise of SpaceX happening, and I was kind of paying attention to that and watching that. When we got to see, I think it was Orbcom 2, whichever one it was, so they first successfully landed the booster, I was like, that's pretty exciting. I want to be doing cool stuff like that matters, makes a difference. So I kind of got drawn in there, and I guess we all just want to bring to life the likes of Star Trek. So fundamentally, I guess it's a love with the industry as much as it is anything specific on the business of space.
And my final question, which I call my Geordie LaForge question, which is which Star Trek? You've got the original, you've got TNG, is there a specific series that is close to your heart, or do you love all of them?
I like a lot of them. I feel like maybe controversial, but the recent ones, Star Trek, Strange New Worlds with Anson Mount, I'm liking a lot of what they've been putting out with that one. So that one definitely has been good.
I'll have to revisit it. I do model my hair off of him, so I've got that. I've got that down.
This is a little more gray, I think.
It is a little bit more gray. Yeah, that's coming. That's coming. And if anybody wants to get in touch with you, how could they do that?
Yeah, so we have a website, astronsystems.com. On there, we have an email listed, hello@astronsystems.com. Feel free to send in an email. I'm also on LinkedIn. I'm sure you can find me. There's, again, the link on our website somewhere to my LinkedIn. So we're very open to being contacted. So, yeah, reach out.
Fantastic. Well, thanks, Eddie. Really appreciate your time. Congratulations to your team, and look forward to further conversations soon.